Hello. In this video, I'm finishing section 2.3, Introduction to Functions. So we saw many ways, different ways to describe a function. Essentially, any relation is a set of ordered pairs, and a relation is a function if no x value matches with two different y values. Or another way to say it is that no x value is repeated. So one way to determine whether a graph is a function is by using the vertical line test. Okay, that's page 207. If every vertical line intersects the graph of a relation in no more than 1 point, then the relation is a function. So I'm going to go over the example that we did with the graphs, and we will determine whether the relation is a function. So this on page, this definition of the vertical line test is on page 207, and we're doing example 4. So use the vertical line test to determine whether each relation graphed in example 3 is a function. And I will copy the relations from example 3. Let's copy those. Okay, these were the relations from example 3. Okay, so let's read again. If every vertical line intersects the graph of a relation in no more than 1 point, then the relation is a function. The first relation consists of 4 points. So we can see that every vertical line intersects the relation at no more than 1 point. And we can have some vertical lines that don't intersect at any point. So A is this is a function. Let's write a note. In A, the relation is a function. Because every vertical line intersects the graph at most 1 point. But B, that one is not a function because you're going to have some vertical lines where the vertical line intersects the graph at only 1 point, but you're going to have some other cases like this one. It intersects the graph at more than 1 point. So in part B, the relation is not a function. In part C, every vertical line will intersect the graph at most 1 point. So that one is a function. And D, that's still going to be a function. Every vertical line intersects the graph at 1 point. So that one, okay, let's see. Just want some space to type. Yeah, so this one is a function. Only part B, where the graph, where some vertical lines intersected the graph at more than 1 point. Only in that case, the relation wasn't a function. So I mentioned last time in the last video that the most important, at least in this course, the most important way to represent a function is by an equation. One example is y equals, let's write the equation, y equals 2x plus 1 is a function because each x value corresponds to exactly one y value. So there's no way to obtain two different y values for the same y or for the same x given this equation. On the other hand, x equals y squared, that one is not a function. So this one is not a function. Because for the same x, you have different y's. Let's set up x equals 1. We know that y squared equals 1 has two solutions. And those are plus minus 1. So you have an x value corresponding to two different y values, or x equals 4. That also has two solutions. So you have two different y values for the same x. Okay, so we have seen different ways to describe a function. And I'm going to copy the variations of the definition of a function. So I mentioned this last time. That's on page 209. A function is a relation in which for each distinct value of the first component of the order pairs, there is exactly one value of the second component. You can also say that a function is a set of order pairs in which no first component is repeated. And another way to say it is that a function is a rule of correspondence that assigns exactly one range value to each distinct domain value. Now, notation. If y is a function of x, it is written y equals f of x. And that notation, y equals f of x, this reads either f of x or f at x. Okay, so we're going to evaluate functions. We will evaluate the function and simplify. The function is f of x equals x squared minus x minus 5. We are going to find and simplify. Find and simplify f of 2, f of negative 1, and f of a plus 1. So let's start with f of 2. So what we're doing is substituting 2 for x. That is, we're going to substitute 2 for x, so we have 2 squared minus 2 minus 5. We substituted 2 for x. 2 squared is 4. And 4 minus 2 minus 5 is negative 3. F of negative 1, we substitute negative 1 for x. And that's going to be negative 1 squared minus negative 1 minus 5. Negative 1 squared is 1. Minus negative 1 becomes plus 1 minus 5. This is also negative 3. And f of a plus 1. Now the input of f is no longer x, it's a plus 1. So this is a plus 1 squared minus a plus 1 minus 5. So that is correct, but we're going to simplify. We're going to simplify a few terms. We can distribute that minus sign, and we can square a plus 1. A plus 1 squared is a squared plus 2a plus 1 minus a minus 1 minus 5. So let's combine like terms. A squared, there's nothing to simplify. Plus 2a minus a is going to be plus a. And 1 minus 1 minus 5 is going to be minus 5. Okay, and that's it. Now we're going to evaluate. So we're going to go over example 7. I'm trying to find this example in the book. There it is. This is page 210. We're going to evaluate f of 3 for each function. So we have 4 functions representing different ways. The first one is an equation. The second one is a set of ordered pairs. The third one is a correspondence between 2 sets. And the last one is a graph. So to find f of 3 in A, all we do is plug in 3. So f of 3 is 2. In B, we can see that this function contains the point 3, 1, and f of 3 is equal to 1. The x value is 3, the y value is 1. In C, know that 3 corresponds to 5. And D, one point on the graph, the function passes through, or the graph passes through the point 3, 4. So that's 3. It passes to 3, 4. That's 1 point on the graph, so f of 3 is equal to 4. So sometimes an equation is going to be a function, but it's not going to be given as f of x equals something depending entirely on x, or y as something depending entirely on x. So I'm just going to read this part. I'm not going to copy it. Let's suppose that an equation involves x and y. Assume that y can be expressed as a function f of x. To find an expression for f of x, use the following steps. First, replace, first solve the equation for y, and then replace y with f of x. So that's what I'm doing. That's what we're doing in the next example. We are going to rewrite y as a function of x. Then, once we do that, we're going to find f of 2 and f of a. The first equation is 2x plus y equals 5. Okay, there are two steps. We're going to solve this equation for y, or isolate y on one side. That's not a problem. We subtract 2x from both sides, and y is minus 2x plus 5. So this equation, as a function of x, is going to be f of x equals minus 2x plus 5. And then we can evaluate f of 2 and f of a. Now, f of 2, it's negative 2 times 2 plus 5, which is negative 4 plus 5, or 1. And f of a, there's not much to do. We're just going to replace a for x. So f of a is minus 2a plus 5. And part B, we're doing the same thing. We're rewriting this equation as a function y of x, as a function f of x. And we're going to evaluate f of 2 and f of a. Okay, so we need to solve for y. Let's first isolate the expression with y, in this case 3y, by subtracting 2x squared from both sides. And then divide both sides by 3. So that's going to be what? That's going to be negative 2/3 times x squared plus 4/3. And f of x it's the opposite of 2/3 x squared plus 4/3. We can evaluate this at 2. If the final result is a fraction, we're going to leave it as a fraction. So this is the opposite of 2/3 times 2 squared plus 4/3. But 2 squared is 4. And 4 times 2 is 8. And negative 8/3 plus 4/3 is going to be negative 4/3. F of A is actually easier, even though it has letters. F of A is the opposite of 2/3 a squared plus 4/3. And the last part is when a function is increasing, decreasing, or constant. So I'm going to copy all this information and show you graphically what that means. Suppose that a function f is defined over an open interval I, and x1 and x2 are in I. Part A, f increases over I whenever x1 is less than x2, f of x1 is less than f of x2. Graphically, its graph is rising from left to right. Okay, so an increasing function has a graph that rises from left to right. F decreases over I if whenever x1 is less than x2, f of x1 is greater than f of x2. And the graph of the function is decreasing. And f is constant over I if for x1, if for every x1 and x2, f of x1 is equal to f of x2. A constant function has a graph that is a horizontal line segment. Okay, so f is constant. Whenever the graph is a horizontal line or line segment. Okay, so we're doing 2 examples about increasing, decreasing, and constant functions. Yes, that's one part, and we're doing number 88. Okay, so we will determine the largest open intervals of the domain over which each function is increasing, decreasing, and constant. And we're looking for the domain, so we're looking for x values. So this function is increasing over and we're looking for open intervals. So everything has a parenthesis. Don't worry about brackets, it's everything with parentheses. Between -3 and -1, the function is rising from left to right. So this is increasing over -3, -1. The function is decreasing whenever the graph falls from left to right. So that's going to be decreasing. We're looking for open intervals. Everything is going to have parentheses. That is decreasing over -1. And this arrow pointing to the pointing down and to the right indicates that the graph will continue falling to the right. So that is decreasing over -1 to infinity. And part C, we have a ray that is this horizontal line portion pointing to the right. So that is constant over -infinity to -3. So when they are asking you for the open intervals over which the function is increasing, decreasing, or constant, always look for x values. And the last example is an application. Number 94, that's going to be an application. So I'm going to copy the statement. And I'm going to copy the graph. So there's that. And let's copy the graph. Okay, so a ball is thrown straight up in the air, into the air. That's on page 218 as well. The function y equals h of t in the graph gives the height of the ball in feet at t seconds. And it says, note, the graph doesn't show the path of the ball. So that's not the path of the ball. That's the height a long time. So that's the height in the initial height after 1 second, 2 seconds, and so on. The actual path of the ball would be something like this, thrown straight up and then falling down. Okay, so we have several questions. The first question is, what is the height of the ball at 2 seconds? So we need to interpret this graph. The first tick mark is at 64, but there are 4 parts, so 64 over 4 is 16. So, and we have values like 16, 32, 48, and so on. So at 2, we have 192, and then they are increasing by 16. So that's 192, 208, 224, and 240. Okay, so the graph passes through the point to 240. So the height of the ball at 2 seconds is 240 feet. Question number 2, when will the height be 192 feet? We can identify 2 values. That's what? That's 1 192. And 5, 192. Okay, so that's going to be after 1 second and after 5 seconds. That's B. I'm just going to type it. After one second and after 5 seconds. Part C, during what time intervals is the ball going up and down? In other words, when is the function increasing or decreasing? Okay, so we can see that there's a turning point at 3, 256. 3, 256. Okay, so in the interval, during what time intervals? In the intervals 0, 3, and 3, 7. No, in the interval 0, 3, the ball is going up. That is, the function is increasing. The function representing the height along time is increasing. And in 3, 7, or that's right, 3, 7 with let's keep everything in the homework. They are going to ask you for open intervals, so let's keep it open. And in 3, 7, the ball is going down. So we can see that the turning point occurs at 3, 256. So the ball, the maximum height is going to be 256 feet. And it reaches, and the ball reaches its maximum height after 3 seconds, or at 3 seconds. And after how many seconds does the ball hit the ground? So we saw that the height is going to be 0 at equals 7. So that's going to be after 7 seconds. So this is it. With this, we finish section 2.3. Thank you for listening.